Alright, so today we're going to solve two-sum, and two-sum is asking us to return the indices of two numbers such that they add up to a target. So for me, the most intuitive way to solve two-sum is using the brute force approach, and before I ever saw any solution to two-sum, I had the brilliant aha moment of using nested for loops. So the idea using example 1 here is that you have a for loop that starts at 2, and then you have another for loop that starts at 7, and it goes through each value, and it adds each value to the first one, and it sees if it equals the target 9. So that's a pretty straightforward and simple way of solving two-sum, but it's not the quickest way. Just to write out the code for that, we have for I in range of the length of our array, and then we have for j, and we're going to start at one position above our first for loop, and then go through the rest of the array. And then we're going to see if the position at j equals the target minus nums I. That's an if statement, and if it does, we return those indices. So looking at the time complexity of this brute force approach, we have O of n for our first for loop because it just iterates through the array, and then our second for loop is also O of n. But since our nested for loop runs through each value of the array, it's going to be O of n times O of n. So it'll actually be O of n squared. So there's definitely a better way to do this, and the better way to do that that's more optimized is by using a hash map. And we can use a hash map by first storing all the values of our array inside of it. So the code for that would look something like this. We'd have our hash map. And what we'd want to do first is store all the values of our array and their indices in that hash map. And then once we do that, so just to draw that out actually, so say for example 1, we had 2, 7, 9, and 11. In our hash map, we would store 2 would be 0, 7 would be 1, 9 would be 2, 11 would be 3. So we have our key, and then we have our values. So these are key value pairs. So to do this using code, we iterate through our array again using a for loop. So for I in range, length of our array, we want to go through the whole thing. And now this time, we're going to use our hash map to store our key value pairs. So we'll take hash map, and then whatever the first value is, second value, third value, and so on, we're going to set that equal to the indice. So you can kind of see where we're going with this. Basically, what we're going to use the hash map for is we're going to very quickly look up in our hash map if a number exists such that it is a complement to whatever value we're iterating through such that it's equal to our target. So just to make that a little bit more clear, we're going to be looking for the complement number to nums I. So if we're iterating through each value in the nums array, we're looking to see if any of these numbers are such that are equal to our target. So mathematically, when we write that out, and we're trying to find a complement number to num's I that's equal to our target, we can basically say our complement is equal to our target minus num's I. So in the case of our target being 9, we're looking through this array to see, or through this hash map, to see, okay, if we're at 2, and our target minus 2 is 7, and our complement is 7, and we're looking in our hash map to see does 7 exist. And it does. 7's right here. And so now that we know that it exists, we're going to return 0 and 1. And so using a hash map, the code for that would look something like this. We're going to iterate again through our array, and we're going to say for I in range of our array, the complement is equal to target minus num's I. So that's our math. And then if our complement is in our hash map, and the hash map complement does not equal I, we want to return I in the hash map complement. And so this is much faster simply because we are not having to iterate through the array and then each subsequent value in the array for every value in the array. So just analyzing the time complexity here, we're only traversing our array twice, and that's it. The hash table or our hash map reduces our lookup times to O of 1, and the overall time complexity would be O of n, since we are only traversing our array technically twice, but each time it's going to be O of n. So overall it's O of n. And now there is even a faster approach to this where instead of having to populate our hash map and then use another for loop to search through it, we can do what's called a one-pass hash map where we're iterating and inserting elements into the hash table. So we'll look back to check if the current element's complement already exists in the hash table. If it exists, then we know we found a solution and we return the indices immediately. So something like this would look like similar to what we did before. We have our hash map, and it's equal to nothing right now, but we're going to loop through our array. And then we're going to have the same logic. We're going to try and find our complement to where we currently are at the array. And complement is equal to our target minus the current position we are in the array. And if that complement is in our hash map, And we are simply going to return the hash map I and the hash map complement. And if not, hash map, the position of I in our hash map simply equal to I. So that way we at least populate the hash map. So this time complexity is also O of n, since we're traversing the list one time with our for loop. And then it's actually a little bit faster simply because we're only doing one lookup in our hash map. Well, we're only traversing the array once, and we were doing one lookup in our hash map before. So